Surfactants are molecules that reduce the amount of surface tension of a liquid. The name itself is a contraction of the words surface active agent. They are amphipathic. This means that they are made up of a polar head and non-polar fatty acid tail. To understand how surfactants work in the human body, first we need to understand how they are able to reduce surface tension. Surface tension is a result of the cohesive forces between liquid molecules. Take a drop of water, for example. Water molecules in this drop are held together by strong intermolecular forces in the form of hydrogen bonds. While these forces will sometimes push and sometimes pull at adjacent molecules, they will balance out until an equilibrium is reached. There is an overall net attraction between these water molecules. However, water molecules at the surface of the water experience an unbalanced force of attraction with its adjacent molecules. These surface molecules will thus be more attracted towards the center of the water droplet and will move accordingly. This causes molecules to pack more tightly at the surface, thus more surface tension is produced. When surfactant is added to water, their hydrophilic heads are attracted to water, but their hydrophobic tails are repelled. They thus align themselves along the surface of the water droplet with their tails facing outward. This breaks some of the hydrogen bonds between water molecules at the surface, reducing surface tension. Natural surfactants are produced in the human body. In the lungs, they are made up of 4 proteins and 6 lipids, and are found in the alveoli. Alveoli in the lungs are often described as grape-like bunches. They are thin and have a large surface area to optimize gas exchange. They are lined with a layer of water molecules on their inner surface. The effects that this water membrane has on the alveoli can be modelled using the law of Laplace. Say there is a hollow sphere made of some pliant material with a thin layer of water lining its inner surface. Intermolecular forces act upon all these water molecules, attracting them with each other. This attraction all around the hollow sphere creates a net force that is acting inwards. If there is gas inside the hollow sphere, pressure will be created until an equilibrium is reached. If there is no gas inside, the hollow sphere will collapse. This same law applies within the alveoli. Upon inhalation, pressure of the inhaled gas allows the alveoli to expand. However, upon exhalation, there is no longer any air pressure to help the alveoli stay intact. Collapsed alveoli are no longer able to perform gas exchange, which would be devastating for the animal. So how do alveoli maintain their shape? This is where surfactant comes into play. Pulmonary surfactant is secreted by alveolar cells and are able to reduce the surface tension of the membrane within the alveoli. This allows the alveoli to stay inflated despite the change in pressure. This reduction of surface tension also makes it easier for breathing to occur, as it lowers the amount of energy required. Surfactant is only produced in the alveoli at around 34 weeks old in a fetus. Premature babies born before this time will have to undergo surfactant replacement therapy. Another area in the body where surfactant could potentially be found is in the stomach, an integral part of the human digestive system. The stomach contains acid with a pH of 2. The components of this acid include hydrochloric acid, potassium chloride, and sodium chloride. These are secreted by parietal cells in the stomach lining. This stomach lining is also made up of mucosal cells that secrete mucus. Mucus coats the cells in the stomach to protect them from stomach acid. This mucus also contains bicarbonate or hydrogen carbonate, a base that reduces pH. As well as this bicarbonate, it has been speculated that there are surfactants in the stomach that help protect stomach cells from the highly acidic stomach acid. These surfactants, in the form of free phospholipids, have positively charged phosphate heads and non-polar fatty acid tails. In the stomach, the positively charged phosphate heads form electrostatic bonds with the negatively charged mucus layer, creating a hydrophobic barrier between the stomach acid and the cells lining the stomach. This is believed to prevent back diffusion of acid into the mucous membrane and keep the stomach lining protected. However, this is still speculation and has not been proved.